going to go ahead and keep expanding on what we've learned with stoichiometry, theoretical yield, limiting reactant, excess reactant, percent yield, all of those things in these examples. First up, in the balanced equation below, how many grams of solid iron can be formed if 50 grams of Fe2O3, iron 3 oxide, reacts with 10 grams of CO, carbon monoxide? What is the excess reactant and how much excess remains? It does give us a balanced reaction here. So again, that part's nice. We don't have to. We could just give descriptions or say this is what's reacting, this is what's being produced, and develop a reaction ourselves. But it is giving us the balanced reaction because the focus here is not balancing, it's determining theoretical yield, excess reactant, etc. So first thing I'm going to do is write down what I'm given. I'm told I have 50 grams of iron 3 oxide and 10 grams of carbon monoxide. I don't know what my theoretical yield is. Sorry, my limiting reactant. I have no idea what my limiting reactant is, but in order to answer the question, I have to find that first. So I'm just going to pick one. I'm going to pick iron 3 oxide, and I'm going to say how many grams of Fe2O3 are needed or required to react all of my carbon monoxide. I'm starting off with 10 grams of CO. First thing I need to do is convert to moles of carbon monoxide, because again, I cannot compare grams. A gram of carbon monoxide does not contain the same number of particles as a gram of iron 3 oxide. Add up the molar mass of carbon monoxide, and it's 28.01 grams of CO for every 1 mole of CO. I look at my balanced reaction, and I see that 1 mole of Fe2O3 reacts with 3 moles of carbon monoxide. So I've canceled my grams carbon monoxide, my moles carbon monoxide. I'm now into moles of Fe2O3, but I'm trying to just go straight for grams here. So I add up the molar mass, and it's 159.8 grams of Fe2O3 for every 1 mole of Fe2O3. There is a decimal place there. Again, just making sure my moles have canceled. Now I've got grams. That's good. Complete the calculation, and I get 19.0 grams of Fe2O3. Remember what that means. That means 19.0 grams of Fe2O3 are needed to react all of my carbon monoxide. So I asked myself, do I have enough? And the answer is yes, I do. I do have enough. I have 50 grams, which means my Fe2O3 is my excess reactant, and my carbon monoxide is my limiting reactant. So the carbon monoxide is going to limit how much product can be produced. So to answer the first part of the question, how many grams of solid iron can be formed? That's going to depend on the amount of carbon monoxide I have. So I'm going to use that in the calculation. Number of grams of Fe. I've got 10 grams of carbon monoxide. 1 mole of carbon monoxide weighs 28.01 grams. I see based on the balanced reaction that 2 moles of iron are produced for every 3 moles of carbon monoxide consumed. And then I look on the table and I find the atomic weight of iron, and it's 55.85 for every 1 mole of iron. This gives me 35.0 grams of iron. So I've answered the first part of the question. I can produce 35 grams of iron based on the system. Now, the second part, what is the excess reactant? I've answered that too. I said there's the excess reactant is Fe2O3. But I haven't answered is how much remains. And we're going to need a calculator for this because I definitely forgot to write this portion of the question down. But there's a few different ways we can go about this. Easiest way, we've already figured out that we need 19 grams of Fe2O3 to react all of the CO. We know we have 50 grams of it. So the easiest thing to do is say, well, how many grams of Fe2O3 remain? I've got 50 grams of Fe2O3 H2O3 available. I've got 19.0 grams of Fe2O3 that's going to be used up in the reaction. So the math is easier than I thought. We're going to have 31 grams of Fe2O3 left over. Now, again, I said that we kind of lucked into that just based on the way I solved the question. It is true. If I had solved it the other way and said, how much CO is needed to react all the Fe2O3, I wouldn't know how much Fe2O3 was needed to react all the CO. I would have to redo that calculation. So there's multiple ways to find the excess reactant. Another way I could have done it is I could have said, okay, how I could have converted this amount of iron backwards to Fe2O3 and said how many grams of Fe2O3 is this going to use up? And it would come back to that 19 for me, giving me that answer. Again, what I mean by that is taking this value here and converting that to grams of Fe2O3 needed. That would have given me that 19.0 grams of Fe2O3 needed. The math would have worked out. Trust me, if you don't practice it yourself, but see if you can get there, okay? And I would have still found 31 grams left over. There's multiple ways to do it. We got to figure out what you're most comfortable doing. But you should be able to figure out your limiting reactant, your excess reactant, how much, what your theoretical yield is, and how much excess remains in any question. And then if we give you any actual yield information, you should be able to figure out the percent yield as well. So, percent yield. Let's look at this one. Magnesium carbonate decomposes on heating to form magnesium oxide and carbon dioxide. Suppose that a 50-gram sample of magnesium carbonate was heated and that 20 grams of magnesium oxide was subsequently collected. What was the percent yield of this reaction? First you got to figure out what's going on. You got magnesium carbonate. Magnesium is Mg2 plus, carbonate is CO3 2 minus. So together that must be a 1-to-1 system. This is a solid and it's going to decompose to form magnesium oxide. Again, Mg2 plus O2 minus, so 1-to-1 ratio. And carbon dioxide, which is a gas. I want to find my percent yield, but first I need to figure out my theoretical yield. I can't do percent yield without theoretical yield. So I need to know how many grams of magnesium oxide I could theoretically produce. Starting off with 50 grams of that magnesium carbonate. One mole of magnesium carbonate has a molar mass of 84.32 grams. Based on the balanced reaction, everything's 1-to-1. You still have to show this though, because it's correct conversion. 1 mole of magnesium oxide is produced for every 1 mole of magnesium carbonate consumed. Add up the molar mass of magnesium oxide and you get 40.31 grams of magnesium oxide for every 1 mole of magnesium oxide. And you get 23.9 grams of magnesium oxide as your theoretical yield. So theoretically, perfect reaction, I should be able to collect 23.9 grams. I know I only collected 20, so I know my percent yield's under 100, but that's what I expect. So again, your actual yield, 20 grams, divided by your theoretical yield, 23.9 grams, times 100%. Each number here has 3 sig figs. The 100 is an exact number, so it doesn't limit our sig figs. And we get 83.7% as our percent yield. What's this one? Write the balanced chemical equation based on the following description. Solid phosphorus reacts with chlorine gas to produce the gaseous phosphorus trichloride. Okay, let's do that first. So we have to remember that phosphorus is P4. It's one of our polyatomics. So P4, solid, reacts with chlorine gas. Chlorine is one of our diatomics, Cl2 gas. These will produce gaseous phosphorus trichloride. Phosphorus and trichloride means 3 chlorines. Okay. Now to balance this, I have 4 phosphorus on one side, and you need 4 on the other. That gives me 12 chlorines on one side, so I need 12 chlorines on the other. You got A done. What's B? What is the identity of the limiting reactant based on the following information? 205.1 grams of phosphorus was reacted with 287.6 grams of chlorine gas. Okay. I don't know what the limiting or excess reactant is or limiting reactant is. Let's figure it out. How many grams of phosphorus is needed to react all of my Cl2? I have 287.6 grams of Cl2. 1 mole of Cl2 weighs 70.90 grams. Looking at my balanced reaction, 1 mole of P4 reacts with 6 moles of Cl2. So I see I need 83.77 grams of P4 to react all of my Cl2. So that means that Cl2 is my limiting reactant. I have more than enough phosphorus. It's my excess reactant. Cool. I know my limiting reactant. Let's see, part C. If only 218.7 grams of phosphorus trichloride were collected, what is the percent yield of the reaction? Now, to do that, I need the theoretical yield. And I don't have the theoretical yield, so I'm going to have to find that information first. So how many grams of PCl3 can I produce? I've got 287.6 grams of Cl2, and I know that's my limiting reactant, so it's going to limit how much I can produce of my product. 1 mole of Cl2 weighs 70.90 grams. Looking at my balanced reaction, 4 moles of PCl3 are produced for every 6 moles of Cl2 consumed. Again, it's always good to kind of just check to make sure grams of Cl2, moles of Cl2, grams of Cl2, moles of Cl2. Definitely forgot to write the last step up there. I apologize. Let me fix this stuff up here. Sorry about that. Behind the scenes, I have a cat that's very insistent on my attention right now, and it's taking up part of my attention, just trying to keep her claw to my leg while she asks for attention. So I apologize. That should be times 123.9 grams of P4 to 1 mole of P4 to get those to cancel out. And that's how I got the 83.77 grams of P4. Okay, my PCl3 weighs 137.3 for every 1 mole. Calculate this out. This gives me 371.3 grams of PCl3. Again, there's your theoretical yield. All things perfect, no questions asked, I would get 371.3 grams. I didn't. I only got 218.7. So let's check our percent yield. I have 218.7 grams of PCl3 that I actually collected. My theoretical yield is 371.3 grams of PCl3. Multiply that by 100%. And I get 58.9% yield. Okay. Part D, how much excess remains after the reaction has been completed? I do have very little need of space, but I do need a little bit of space to write this down. The advantage here is we know that we have 205.1 grams of P4 available. But I know that 83.77 grams of P4 will be reacted with the Cl2 to produce the PCl3. So overall, I have 121.3 grams of P4 remaining. Balanced reaction, limiting reactant, percent yield, and amount of excess reactant remaining after the reaction is complete. So I think that this picture best describes the way you should feel when you're working these problems. You should be asking yourself these questions. What is the limiting reactant? What reactant is in excess? How much excess reactant is left over? What is the percent yield? What is the atom economy? Now, I particularly am not going to ask atom economy on quizzes or exams. Okay, so if you want to skip that, that's fine. But it's a good idea to think about in the world of sustainability, and that's the way our world is going. We're trying to, make sure that we are doing things the right way for the way the earth and the people need it. So it's a good idea to think about behind the scenes, but I won't ask it directly. All of these help answer though, all of these questions above. The whole point of all of these is to answer this question. Is the reaction worth completing as designed? Should we find a different preparation method? You should be able to design questions like this. Pick any reaction, go to your textbook, pick a reaction, give each reactant some value, some amount of reactant to start with. Determine the limiting reactant, the excess reactant, how much excess remains. What is your percent yield? Give yourself an actual yield. Lots and lots of practice on these problems.